Why is this not showing up? Not much to do today, except the Python Lab 6, the last one. Where do I connect this? And I get less and less people. Oh, no. I hate it when it does that. There we go. There we go. So for today, we're gonna do Python Lab 6. If you download, hopefully this is on the bright space. The one that says there should be hopefully one that says incomplete. There might be a complete one, don't look at it. And I want the one that has, empty here, KF, this Sayeta, XY, and so on. And what we are going to do is, I'm actually not gonna solve it right away. I think you'll start. You can work in pairs or you can work on your own, and then I'll just walk around, help you a little bit, and then I'll come back and solve it at the end. But I'll let you struggle with it for a little bit, ask me questions as I go around, and then yeah, I'll do it at the end. No, because I did for the elasticity, but a couple of things I would check that up. Last time I did transfer this yeah, so that yeah, so this one here is quadrilaterals is not gonna work. We did the example one. That should be and the small changes. Small but very important.
Don't we have we like some period like allocated for 5 minutes? So we don't have anything going on for the 5 minutes. That's right. Yes.
I find that and
Next Friday.
no, actually the next Friday, I think next year was you get to work on the project. If you haven't done the project, so next Friday, I'll be here and will be in the lab. And then, yeah, that's so the project is still under.
Not because I can't decide anything on that.
Yeah, but you can have it like that. Like exam. Yeah, everything that has I didn't know but we download the one and then right trace because this integral is very correct. What should the type be? Yes. Yeah, to download the Yes, yes. That would be but here every node really go over every node has slightly exactly so it's going on and then S is just doing the vector, but it's doing because that's actually at some point you have what is what have you but this is that would be for the business program because we have single home now. Here,
every node has two, one node, so there's the next, all the time. There's actually twice the big, there's like two and a half. But one of the we found it, yeah. So yeah, it's just everything has X and Y. Why does the other two these are, there's not actually like, just being number. It's here that these actually, written X and Y. Yeah, just with all the values I think, would it also show red for the least negative? Yes. You can change the options. Options. Or no, where you know where you click on the board, there's like the little L shape and you click the next to it, there's like a little check. Yeah, the look this is you click red, then it opens up a window. And then one of the tabs is the color bar. And then you can do a reverse rainbow that will just make the red to be the most the slow, the smaller. Right, yeah. What do you have? I mean, I think I would rather have it pressure. But I mean, you can, as long as you want the example that you said on the yeah, and yeah, then that one is fine for the analytical. But I want two different things. I want the estimation of the analytical program. I want the more realistic estimate. Now you can have the oh, I don't think Cool, yeah. Good. Good, good. It's good. What? Yeah, you're wearing my. That one applies the fourth vector, so this should be eight, and it should be basically n1 then dx, n1 dy, into dx, into dy. That's how it has, so I think. Yeah, I think, I mean, the way you want to put it in a vector, you will need to repeat n1, so you have to put n1 and 1, equal to and then you have dx, dy, dx, dy, dx, dy. Yeah, it's the same. The only thing that changes is the D matrix. But you know, the astronomic map, the Jacobian, the Jacobian perspective, all of that is the same. The only thing that changes is that if you look at what the looks like, if you use the B matrix for big programs, it's different than the B matrix for induction. And that's because of the gradient that you do. The two conservations is just there is a respect to X, there is a respect to Y, of the first shape function, second one, third, fourth. So it's just that Y four. For example, that I think we for this one is as 3 by 8 because it has there is a respect to X like N1, N1 X 0, N1 3 at N into X 0, into X 0, N 40X 0. And the second row is like 0, N1 Y, and then the last row is sort of like X, like N1 Y, N1 X, Y. So that image is different, but the sporadic plan and the Jacobian calculating gradient of the shape, all of that is the image. That is a that would be the second part. Yeah, you can take it from this one. Maybe scroll down. Yeah, so I mean the images, it's different classes. This version is still. I mean, this is for the triangle. It's 3 by 3. But other exact same thing. That's different. That's what and you can see that this looks different. This one only has factor. That's what each so much of that. Because the points that you are evaluating on the current domain, like the expired, it matters. Yes, yes. Accurate solution. What you are doing is you are trying to integrate. Okay. So how do you integral? You can do the you go to the table. Where to evaluate. I mean that table is designed basically approximately into the best that we can based on having to point to evaluate. So if you only have if you only have one point to evaluate, then the best point is 0, 0. And then the weight of that is 4. And that's the basic. So if you choose any other point, oh, it will, yeah, no, it will be a very bad approximation. If you have multiple points, you have 4 points to evaluate, then the best points are points like seven, like all four. But here, you only you can do this integration, just a simple point. You're like the best ability to all.
All right. I will fill out some things to move you along. First thing, so the size of the Stevens matrix and the force vector, we're gonna initialize this with zeros, and then what is the size? I think you were getting it correctly. So this should be 2 times the number of nodes, times 2 times the number of nodes. And the reason for that is that every node has an X and a Y displacement that we want to solve for. So there's 2 unknowns per node. So the overall size of this should be twice the number of nodes. For the fourth vector, it's a vector of 2 times the number of nodes. That's the first thing. Then our usual for loop over elements. This I do every time. Just read out the connectivity. Then you get the nodes that make up this element. Once you have these nodes, go get the XY coordinates. And then we have to do the integration. And then you can either do full integration, you will have to evaluate at different psi eta points that you get from the table. And those are the minus 0.57, 0.57, so on. But to make it simple, we're going to do reduced integration. For reduced integration, the point to evaluate is 0, 0, psi eta 0, 0. Some of you were asking, does this change the isoparametric map change between this and the heat transfer problem? That doesn't change. Actually, all of this part up to, even up to here, all of that actually is the exact same thing that I did for the heat transfer problem, because all we are doing is evaluating XYs, evaluating the Jacobian, the inverse of the Jacobian gradients. That doesn't care if you are solving the heat transfer problem or you are solving the elasticity problem. You're just calculating, basically the gradients of the shape functions. So that one you can copy from the previous lab. I'll just try to write it very quickly. So just N1 psi eta. So this will be N1 psi eta times X1, and then N2 times X2, and 3 times X3, and 4 times X4. And then for the Y components, I should just go and try to find what I wrote last time. But yeah, this doesn't change at all with respect to the previous one. For the Jacobian, dx d psi is just the derivatives of this with respect to psi. So this is just going to be dn1 d psi, dn2 d psi, dn3 d psi, dn4 d psi. And then the next one is the same, but with eta. So dn1 d eta, dn2 d eta, dn3 d eta. Then same, but with y's. So y, 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 y. and then y, y. So that is really just the same as before. This shouldn't change from what I did for the heat transfer problem. It's just sum of derivatives of the shape functions times nodal values. Then given those derivatives, you have the Jacobian, and we need the inverse Jacobian to calculate gradients with respect to xy. So the gradient of the shape function with respect to psi eta is just derivative with respect to psi and eta. But if we want gradients with respect to xy, what we need is to multiply the inverse of the Jacobian times this gradient with respect to psi eta. And again, this is the same as I did for the heat transfer problem. So the gradient of N2 is just the inverse times the gradient of N2 with respect to psi eta. The gradient of N3 with respect to xy is just the gradient Jacobian inverse times the gradient of N3 with respect to psi eta. And the last one is just J inverse times gradient of N4 with respect to psi eta gives you gradients with respect to xy. Again, the Jacobian inverse allows you to go from gradients with respect to psi eta to gradients with respect to xy. And again, this is all the same as it was for the heat transfer problem. The thing that changes is the B matrix. This one is the main change, because the B matrix for the heat transfer problem, that one would be a 2x4 matrix, and it will just have dn1 dx, dn1 dy. So it's just basically derivative with respect to x and y. For the elasticity problem, well, we need a matrix. And this one has the funny structure, right? So this one is actually dn1, well, I don't have it as dn1 dx, but this would be the first entry. So this grad n1 xy0, this will be grad n1 xy is the gradient of the first shape function with respect to xy. It has two components. It has the x and the y component. If I do the bracket 0, I'm getting dn1 dx, so the first component. Then 0, then I need grad n2, 0 component, so this will be dn2 dx, then 0, then dn3 0, that would be dn3 dx, 0, dn4, because I have 4 shape functions, 0. So again, this is the first row is dn1 dx, 0, dn2 dx, 0, dn3 dx, 0, dn4 dx, 0. Then the second row for the elasticity problem is 0, and then dn1 dy, 0, dn2 dy, and the dy is because now I'm doing bracket 1. Again, grad n1 xy has both components. It has the dn1 dx in the 0 and then the dn1 dy in the y. So that's why I'm using the bracket 0 here for the derivative with respect to x, the bracket 1 to get the derivative with respect to y, 0, then 3, 1, 0, and then 4, 1. So again, this is the second row is 0, dn1 dy, 0, dn2 dy, 0, dn3 dy, 0, dn4 dy. And the last row is the dn1 dy, comma, dn1 dx, comma, dn2 dy, comma, dn2 dx, comma, dn3 dy, comma, dn3 dx, comma, dn4 dy, and then finally dn4 dx. So again, this should be, I don't think I have the notes open, but a marker. But this one is in the notes, in the elasticity notes. Again, this is different from the heat transfer. And then I defined it for, I don't know if I wrote it down for the quadrilateral, but I definitely put it down for the triangle. For the triangle, it looks just like that, but it ends with 3 shape functions. There's only 3 shape functions for the triangle. So the only thing that changes here is I added 2 extra columns for because I have 4 shape functions. But does that make sense? All right, so that's the B matrix. Then once you have the B matrix, then the element stiffness matrix is just, technically you are summing because this is the integral, and is the weight of the integration point. I don't think I defined it before. But if you do reduced integration, what is the weight of the integration point for a single point for the quadrilateral? Four. And so here I need the weight of the integration point times the determinant of the Jacobian times these 2 things are because of the integration. So this is the weight of the integration point and the determinant of the Jacobian. That's from the integration. Like I said, typically if you have multiple integration points, you will have this plus equal because you will be adding to it. But because we have a single point, then we don't need the plus equal. And then the last thing, which is the actual function that we want to integrate, is just the B transpose times, put it here. So this matrix is integral of BE transpose times D times BE. That's what we want to integrate. BE transpose times D times BE. So here, all I need to do is MP dot BE transpose, and then times D times BE. So BE transpose times D times BE. I need to integrate that. That's where this weight and this determinant come from doing the integral. So that's it. That should take care of the stiffness matrix. Questions? All right. So for the force vector, I have this. I'm also going to integrate it. So I also need to do the integral of this omega squared times xy plus yj. So just omega squared is because the force is basically this thing is rotating and I have some force that is radial. And then how do I get the different components? So the first 2 should be basically integral, replace integral. For now, let me just put, I need to integrate, for this one, I need to integrate n1 times bx. I'll replace this in a sec. For this, I need to integrate n1 times by. Here I need to integrate n2 times bx. Here I need to integrate n2 times by. And 3 times bx, and 3 times by, and 4 times bx, and then 4 times by. That's what I need to integrate. Now, how do I do integrals? Again, what I'm gonna do is I'm gonna do the weight of the integration point times the determinant of the Jacobian times the function that I need to integrate, which is n1 times bx, and bx, I'll do it in 1 sec. I'll just leave it as bx. I'll compute it in 1 sec. Right, but this will calculate the integral for a single integration point. So again, this is the same, but with by. Now this is the same, but with n2. This is the same, but with n2 and by. This is n3. This is n3 and by. This is n4. And finally, this is n4 and by. And now I just need to define what bx and by are. But I have it here, right? So bx is just going to be the omega square. So omega square times the x, and then the by is just going to be omega squared times the y. So this is just a force pushing out in the x and the y direction. This just comes out of this. All right, so that 5 minutes, good. Any questions about that? The key thing is that what do you need to integrate? You need to integrate n1bx, n1by, n2bx, n2by, n3bx, n3by, and so on. And how do we do integrals? We need the weight of the integration point, the determinant of the Jacobian, and then the function that we want to integrate. In this case, single integration point, so you don't need to sum. Otherwise, if there were multiple integration points, you would need a plus equal here. So you would need to add as you evaluate the different integration points. But single integration point, there's no need to continue adding to the sum. All right, so that takes care of the stiffness matrix, that takes care of the force vector, and now doing the assembly. So we need to assemble both the K and the F. This one is a little bit tricky. I don't know if I did it for the triangle. Yeah, I've seen it for the triangle, but this one is the nice one. So what should I have here? This one actually does have it. So has anyone done this one? So what are the entries for the K? No. So Ni and J are, you can see here that Ni, for example, will be 0, 1, 2, 3, and J will also be 0, 1, 2, 3. But here, if I were to put for the heat transfer problem, this was Ni and J. That was for the heat transfer problem on the KE, it was Ni and J. And that's because for the heat transfer problem, there were only 16 entries, like a 4x4 matrix. But now this is not true. The KE, what is the size of KE? 8 by 8. So this will not access all the entries of KE. So this will not work. What should I do? Remember that for every node, that's why there is an extra. For every node, there is X and Y. So for Ni, that goes from 1 to 4 or 0 to 3. For every node, there's another for loop because now I also want X and Y. And then again, for every node J, there's also an X and a Y. So I somehow need to use that. Any ideas? I mean, you also need node map. Definitely you need the node map here with Ni and node map here with Nj, but I need to use the core I and core J. this is what we use for the heat transfer problem. If you look at the heat transfer problem, this is what it should look like. Basically, Ni and J maps to null map Ni, null map and J. Yeah. Almost. Yeah, I mean, you will. There's still one thing missing. Correct. So now this will loop over. Now this will access all 8x8 entries, because it's for every Ni, it will access the core I 0, 1, so XY. Again, the reason for this times 2 plus core I is because now for every node there's 2 entries. So that's why I need to multiply by 2 and either go to the core I 0 or core I 1, so X or Y. This is really the key. And again, this looks different from the heat transfer, for which there's only a single unknown per node. So it doesn't have the times 2 plus core I or the times 2 plus core J. If you go back to that one, it should just have Ni and J, and then node map Ni, node map and J. Lastly, for this one, all we need is just this plus equal Fe, then Ni times 2 plus core I. And that should be it. And then, well, that one. Here it says that there's 64 nodes that are in the inner boundary. Therefore, if there's 64 nodes that are on the inner boundary, I need to fix 128 degrees of freedom, because I'm gonna fix both the X and the Y. And this is just 2 times n node minus that NE. The DE is just zeros, that's it. The rest you can just run, and then it should produce the correct result. And that's it. But the key last thing was this times 2 of the number of nodes. Again, because we are fixing X and Y. All right, I think the completed one is already up there. So I just want to walk through it. So I'll see you on Monday for review. And then we can talk about projects. I can answer questions about the project. Yeah.
Actually, we have homework 6.
Oh yeah, we will have homework too. Again, it's gonna be small, short and sweet. Not yeah. Hello.
It's due on Monday.
It's due Monday, and it's bonus. So you don't accept the last problem.
Great.
Yes,
Mandatory problem 1 and 2 of those.
correct.
Okay.
Yes.
The due date hasn't been out there in grade school the last time.
Okay, I did reply to KU and ask him to change it, but I'll ask it. I mean, we'll change it. It's due on Monday. Yes. And yeah, 1 and 2 are bonus points, homework points. And yeah, problem 3 is mandatory. Yep. So
A couple of questions for you. First, has exam 2 been graded yet?
no,
Okay. Just
I need to get, the thing is, where do I stop recording here?